what we have done is that we have defined a random variable as a mapping from the set of events to the real line. So, we got a real variable. From events we have now got a real variable which we call random variable, which takes values between minus infinity and plus infinity. Now the moment we have a real variable, we can define other real variables which are functions of that variable. The moment we have a random variable x, we can define another random variable which will be, let us say, x square. So, the question is that if we know what we are going to see today mainly is, if we know the properties of x as a random variable, we know it's by properties we basically mean if we know its distribution function, if we know its density function, can we calculate the density and distribution functions of the variable y, right? And we can extend this concept saying that if we have one random variable x, why not have two random variables x and y? Then what is their joint statistics? That is, what is the probability that this and this occurs at, that is, x is less than 2 and y is less than 3? That is a valid problem. We can in general extend it to n variables. See, the moment we can do that, we can talk about vectors, that is random vectors, because each component is going to be a random variable. So, just so that we are able to talk about things like, states and multivariable things, so we should know that if we have more than one random variable, how to handle that. Then once we have more than one random variable, we can also define a function z which is a function of x and y only a function of x. So we can also talk about such variables. So as we are gradually advancing, we are trying to see that from the basic idea how we can get the various other cases which are also going to be of interest in this course, right. So we will talk about these things today. So the first thing is that let y equal to gx. X is a random variable. Remember that g is deterministic. G is there is no uncertainty about g. So y is equal to half x square. That operation of half and that squaring the random variable, these operations are not uncertain. It is x, it is the value which is the argument of the function which is uncertain, right. For example, if you have y is equal to x plus c, where that is also a function of x, where c is a random variable, not x, in that case the function itself is random. There is a subtle difference. We are not talking about random functions, we are talking about deterministic functions of random variables, right. So now the question is, obviously these are our objects of interest. The moment we define another new random variable, we would like to know what is its distribution function. So we'll always go back to the definition. For any random variable, its distribution function is actually defined as the probability that y is less than or equal to y. That is how the distribution function is defined. So what is y? Nothing but gx. So it is the probability of having an x. So now we are transforming from the set of y's to the set of x. We are now, it is the same as the probability of finding out an x or all those x's for which gx is less than or equal to y, because y is less than or equal to gx, rather y is equal to gx, correct. Or you can even go back to the events themselves, or you can say that it is finally, because finally it is the probabilities are coming out of experiments or outcomes of events, that is the basis. So you can also say that finally it is the probability of those events such that corresponding to those events, if you have the random variables x which are functions of xi now, and corresponding to those x's whatever is gx xi, that is less than or equal to y. So we can now, if you have gx xi, this g and x, these two mappings you can club, and you can say that it's a new mapping from the set of events to y. You can also say that. So you can say that it is y is a new mapping which is which gives me the new random variable. Any random variable is a mapping from the set of outcomes to the set of reals, right. So you can define a new mapping y. This is just to bring down the physical meaning of the quantity. The physical meaning of y remains the same here. It is the probability that that value y comes from. For example, suppose you are saying that you have connected a voltage source to a resistor. Now, if you arbitrarily pick up a resistor, let us say 5K nominal written, it is not going to be 5K, it is going to be random. Suppose we imagine that the value of the resistance is a uniformly distributed variable. So then R is the random variable which here works as X. Now you can define, you can ask so many other questions. You can say what is, obviously if you connect a random resistor to a constant voltage source, which for the time being I am assuming not to be random, in general that itself is also going to be random, then you can also ask what is the current. That is going to be a random variable and it is going to be a function of the R. You can ask what is the power. So this is why you see, once you have something random at the basis, you need to determine several derived quantities. This is a very common requirement. That is why we are studying this property, right. So, and there are certain properties that this function g should satisfy. Otherwise, it will not be. If you just take any function g, then it will not be giving you a standard variable y, right. For example, if you take, for example, suppose you take g as the root function, then root over of a negative quantity is not a real. So therefore, corresponding to all negative values of x, you will not get a y. Now the point is that those negative values of x may have some probability associated with it. So then all the probabilities of y will now not add to 1. So there will be some probabilities which will be left unexplained, right. So therefore you need that the domain of this function must include the range of x, right. Similarly, this is that that standard technical requirement of the underlying field being what is called a Borel field. These are some high mathematics, we don't need to understand it, but it says that basically the set of x's which constitute a valid event, you should be able to always form by countable union and intersection of intervals on the real line. This is a requirement, because if you in some very pathological cases you can dig up a function which will not do this, and then you can show that you cannot define a probability measure mathematically consistently on that kind of a set. So we will assume that it happens, it will always satisfy in our cases. This is some crooked thing which the mathematicians think up. I mean they are finicky about every detail, they will not leave any possibility anywhere, but this will always be satisfied, so we don't need to so much bother about it. And we are saying that the function should also be so defined that if x goes to, this gx equal to plus minus infinity events, whenever you will get such events, they must have 0 probability. Why? Because again we want that, suppose gx equal to minus infinity events must have 0 probability, because nothing can be smaller than minus infinity, and gx equal to plus infinity events must also have 0 probability, because otherwise, suppose at infinity you have some discrete probability, suppose, that is, then the probability that gx is less than infinity is not going to be 1. So the moment you can go on having increasing values of y and still not get a probability of 1. So these are technical things, but basically what you have to remember is that when you are defining a function of a random variable, you cannot take, ideally you cannot take any arbitrary function, they have to obey certain rules. You have to look at that function and verify whether it's a valid function. Now the question, now we come to the main problem, that is to find, given the distribution function of x and given gx, how do you find out fy, how do you actually compute it, right. Suppose this is the function gx, this side is x and this side is y, and this is fx of x. Okay, I have drawn two graphs. The upper side is the y, so this curve is the gx curve, y equal to gx, and this is the probability density curve of x. X is a random variable, so it has a density function associated with it. This is that. Now we want to know what is the density function of y, right. So I mean, how do we calculate that? So first of all, note that for any given value of x, right, if you take any value of y, suppose this is y and this is y plus dy, you have to find out what is the density function. You have to find out that what is the probability that y lies between y and y plus dy, and then divide that by dy. That is going to give me the density function. It is a derivative of the distribution function. So first thing you have to note is that for a given value of y, there may be many values of x. See, my final first probability must come from x, because I have the description for x. Now it turns out that for a value of y, there are many values of x. This is one value, this is another value, this is another value. So there are three values of x which satisfies y is equal to gx for this value of y. So in general, if you put any value of y, you may get a number of real roots, right. Now that means that now if you change y around that, if you change y to y plus dy, then all these points will now contribute the probability. So then there will be a change on x1 to x plus x1 plus dx1, x2 to x2 plus dx2, and xn in general up to xn to xn plus dxn. In this case 3, here I have written n. Okay. So basically, what is the probability of y plus dy? It is these hatched areas, these pink hatched areas. That is the probability that y lies between y and y plus dy. Now, so that is what I have written, that probability that y is between capital Y is between small y and y plus dy is basically the sum of these probabilities, sum of these hashed areas. Now it turns out that, see, here we have taken a positive increment. Now it turns out that whether dx1, there is a small sign problem which you have to take care of. It turns out that if you have the gradient as positive as it is here the gradient is positive at x1, here the gradient is positive, but here the gradient is negative. So therefore, similarly you have dx1 is positive, dxn is positive, but dx2 is negative, right. Why? That is because dy is equal to, that is simply because dy equal to dxi into g dash xi, and dy is positive. So if this is negative, this must be negative. Now when you are calculating probability, you do not see positive negative. So your probability is actually sigma I is equal to 1 to n fx xy into mod dxi. Whether it is this way or that way, you are going to have probability. So and what is mod dxi? Mod dxi is nothing but dy by mod g dash xy. Now if I take mod here, I can also write this as mod this into mod this, because this is going to be positive. I have taken a positive increment. So it turns out that that the probability that y is between y and y plus dy, which will obviously be by definition this, is given by this into dy, which means that this part is equal to this part. So now you find, see that given the distribution function of x and the function g, if you are given g, you can calculate g dashed. G dashed is the derivative of g. You can calculate fy. So at every point y, solve g equal to that y, find out the roots, then you have to sum at all those roots, you have to compute this, then you will get the density function of y, right. There is a simple this is a very simple example. In the book you will find much more complicated examples. One of the simplest maps that you can think of is a linear map. I mean, strictly speaking, mathematically this is not linear in the sense that it is affine, that is superposition cannot be applied on this. So in that sense it is not linear, but it is the equation of a line. So it is an affine map. So if you have y equal to ax plus b, then what is g dash x? It is a. So now see that what is the probability that y is less than or equal to y? It is a probability that x is less than or equal to y minus b by a. Simply solve from here. See, this is a 1-to-1 map. So then corresponding to every y, we only have one x. So in this case there are going to be only one root. There is no point where you will get n roots, right. So it's a simple case. You need to consider only one point. You don't need to sum or anything. This is a very simple case. So obviously probability that x is less than or equal to this is nothing but this. In terms of the distribution of x, it is this. And if a is less than 0, then there is a problem. Then probability that y is less than or equal to y translates to x is greater than or equal to y minus b by a, because a is negative, which means that it will become 1 minus fx into y minus b by a if a is less than 0. So now what is fyy? It is, we know that it is nothing but, we have to differentiate this. So we differentiate now. What is dy? Dy is a dx. So when you are differentiating with respect to y, it is like differentiating with respect to 1 by a dx, and then dfy we have put this one, we have taken from here. So this is like this if a is greater than 0, and this is like this minus when a is less than 0, because you are now differentiating this one. So here is a minus. So obviously when a is less than 0 minus and a is greater than 0 plus means you can club these two formula and say 1 by mod a. So this is the probability density function of y given the probability density function of x. And you can do this we sort of obtain from common sense principles. Now you can put it in the formula. If you put it in the formula, you will get the same thing. See, we are getting this mod g dash xi is this mod a, and fx xi is this fx y minus b by a. So we are getting the same thing, and we have only one root because of that function. So it is the same thing. Now you can define in exactly the same way the conditional density functions can also be defined. Basically the same thing, because you can follow exactly the same arguments. If instead of calling this as fx given x, if you call this as fx given m, if this is the conditional density function of x given the event m, then also the same exactly similar argument will apply. So the same formula will apply. So f of y given m is going to be related to x, is going to be related to f of x given m in exactly the same way. So there is no change here, and you have the same formula, only here I have put y given m, here I have put x. No change. Yeah. No, x given m means that what is the probability of having a certain x given that some event has occurred. M is an event, right? Okay.
So that event we have already defined, right? That
Nah.
event cannot vary.
Yeah, that is our a priori knowledge.
Okay.
We know that such a thing has occurred, right? For example, we know if we cast a die, then somebody tells me that that an even number has occurred. What is the probability now that a 2 has occurred? This is probability of x given m. Now we talk of more than one random variable, right. So now let x and y be two random variables, they may be related, right. The thing is that they may be related. So that is what makes it interesting. If they are not related, they become, we will see that they become simple products relations. But so now let x and y be two random variables. Now the question is, again, everywhere we are interested to compute density and distribution functions, because once we know density and distribution functions, we know everything about that variable. But I mean, as far as probability is concerned, that constitutes total information, right. But I mean, it actually turns out that that is very difficult and expensive. Not only difficult, it is very expensive to find out probability distribution functions of real objects, simply because you have to perform a large number of experiments. So that is why people, I mean, that is why a lot of things have been done where people try to estimate it using small samples, or people do not, I mean, try not to require the exact knowledge of the density function and things like that. So although we are very simply talking about density and distribution functions, they are practically obtaining density and distribution functions of physical real variables are sometimes very difficult. So but anyway, we will cross those bridges when we come to them. So so here we have, now I am trying to define what is known as a joint distribution function of two random variables x and y, and this is the meaning. So the meaning of fxy xy is the probability that simultaneously x is less than or equal to x and y is less than or equal to y, simultaneously. That is important, right. So obviously what are the properties? That f is minus infinity and y, or f is x or minus infinity, is 0, because y cannot be less than either x or y, none of them can be less than minus infinity. See, both have to be simultaneously satisfied. So it is the probability that x is less than or equal to minus infinity and y is less than or equal to y. So obviously x cannot be less than minus infinity, so the probability is 0, and similarly here. And similarly f of infinity is 1, because x must be less than infinity plus infinity and y must be less than plus infinity. But f x infinity and or f infinity y is not 1. In fact, it will be the marginal distribution, right. So here we can substitute 1 infinity and get a nice number. Here we have to substitute both. Here we cannot substitute 1, then we will not get 1 here. This I hope you realize. So now let us see, many times we would like to know what is the probability that x lies between x1 and x2 and y lies between y1 and y2, given the distribution functions, right. So you see, this is y2 and this is y1, suppose these two lines, and this is x1 and this is x2. So what is the probability that simultaneously, first of all, what are we talking about? We want to find out the probability of this part, right, naturally. So that we have to find out in terms of the distributions. So we first say that it is this area, which is f x2 y2, I am assuming that x2 is greater than x, minus f x1 y2. What is x1 y2? That is this green hatched part, this part, minus x2 y1, which is this part. So now if you have done that, you have actually subtracted this part twice, this part you have subtracted twice. So you should not subtract twice, so you have to make it up. That is why plus fx1 y1. So then what is left is this square, right, very simple. Now we talk about joint density. So far we have seen joint distribution. So how do you get joint density? It is nothing but double differentiation, del x del y, because now I have two random variables, now it is a plane, right. So, so it is del square f x y by del x del y, that is given this one you can find this one in this way, and given this one you have to integrate the density function in this way, that is it will be a double integral now, because you have to have minus infinity to y, because the probability that beta is less than or equal to y. So, it is from minus infinity to y all possible values, and from then from minus infinity to x all possible values. So, it is a double integral that will give you a f of x y, correct. Now, actually what happens is that suppose there are two random variables and you are asking question about, suppose you have a red ball and a green ball, and you are saying what happens to the red ball. You are not asking any question about the green ball, which means that the green ball can be anything. So, all possibilities about the green ball, whatever is diameter, big, large, weighty, all cases are being considered. You are keeping your eyes closed about the green ball. You are only asking questions about the red ball. When you are trying to when there are two random variables which are related and you are trying to characterize the probability of only one, not talking about the others, that is called marginal statistics. I mean, that is the name given to it. So, that means that for all the other random variables which you are not considering, you have to consider all possible combinations for them. So, therefore, if you have a distribution function, for the other argument you have to put infinity, because they can take any value. Therefore, this is what I was saying some times back, that if you put 1 plus infinity, then f x infinity will give you just the statistics of x, and similarly f infinity y will give you the statistics of y. So, so given the joint statistics of two variables, by putting an infinity into 1, you can always reduce it to one random variable, just simply by ignoring the other. Basically, it is ignoring the other. And if you have two random variables which are independent, that is, suppose the two random variables are actually coming from two different experiments. So, the value of one random variable is in no way affected by the other. So, if that is so, then their joint statistics is nothing but this into this, because because the events corresponding to y are unrelated to the events corresponding to this. So, when you have two mutually exclusive events, we know that the probability of A and B occurring is equal to probability A into probability B, and when we have joint density, we are talking about A and B occurring together. So, it will be nothing but the product of the densities, right. Okay.
What will be the order of integration?
Which one?
That integral in minus infinity to x, integral minus infinity to y. This will be d alpha d beta or the other way? D beta is which one you have to?
Obviously, it will be d beta d alpha. But strictly speaking, yeah, because alpha actually I am integrating. This is supposed to be the x argument. This is supposed to be the y argument. So, if this is the y argument, I am integrating this first. So, it should be d beta d alpha.
It
Yes.
does not matter.
That it's a question of notation. It does not matter so much. Mane, obviously, if you I mean the variable you are integrating, you have to take the corresponding differential naturally. Okay. Now take this case that z is a function of two random variables x and y. It can happen. Very common example is z is equal to x plus y. Okay. General example is sum of n variables, weighted sum of n variables. These are very common quantities which we all the time encounter. For example, we regularly average things. So, if you take 3 things and if you compute an average, what you are doing is x1 plus x2 plus x3 by 3. So, what are going to be the randomness properties of this average if you know the randomness properties of the sample? That is a very common question, right. So, we suppose we have this. Can we talk about the density function of this given the joint density of x and y? See, in general, if you are given x and y, if you have two random variables x and y, you need to know their joint density, because they may be related, they may not be related, right. So, the joint statistics is the complete information about those two random variables, right. So, obviously, it is very simple that what is the distribution, that is what is the probability that z is less than or equal to z. Obviously, you will have to integrate this over a region which I am calling dz. What is that region? That region is that this gxy, this region consists of all those xy's such that this gxy is less than or equal to z. So, you have to basically you have to characterize that region and then integrate the joint density function over that region, then you will get the distribution function of fz. You will see this naturally. Are you able to follow this? See, basically what you have to find out, you have to, if you have to get the, you have to get the distribution function. If you have to get the distribution function, you have to integrate the density function. Now, integrate the density function over which points? Over all those points such that capital Z is less than or equal to Z. Now, what is capital Z? Capital Z is gxy. So, you have to consider only integrate over that region of x and y such that g of xy is less than or equal to Z. Only over this region this probability is applying, is it not? Right. And this is another case, that is, if you have a now gradually, once we have something, you would like to have something more. So, once you have defined a z is equal to gxy, then you say that okay, let z be equal to gxy and let another random variable w be another function of xy, which is hxy. Now, obviously, once I have z and w, I can define their joint statistics because they are also two random variables, and since they are both functions of x and y, so this joint statistics must be related to the joint statistics of x and y, because x and y are the basic entities, z and w are basically defined from x and y. So, their joint statistics must be computable from the joint statistics of x and y, right. How to do that? So, again same argument, that is the basic reasoning is very simple. Basic reasoning is that what is going to be this distribution function? It is the probability that capital Z is less than or equal to small z and capital W is less than or equal to small w, right, which means that you have to, now the probability is actually coming from the random variables x and y, because they are the basic random variables, z and w are derived random variables, right. So, we have to now integrate this function over again some region just like here. Now, what is this region now? It is now going to be a different region. Previous region was saying that gxy is less than or equal to z. Now, I have to choose my region such that both these conditions are satisfied naturally, because this means that both z must be less than or equal to z and w must be less than or equal to w. Here there was only one condition. So, now I have to, so basically my region will become smaller, right. So, but anyway still it is a region. So, now I have to integrate it over that region. See, this is sounding abstract, but the moment you solve a problem, go to a problem, as we will go next week, you will find particular examples of G, H. So, immediately by inverse solving you will have to compute these regions, and then if fxy is given, then you have to evaluate that integral. Now evaluating that integral is sometimes maybe difficult, it may involve beta gamma functions, those things are separate, but the basic idea is that the integral must be evaluated over a region, over the appropriate region, that is all. So, that way it is uniform. Now, here what they are doing is that here they are now the question is what you get is actually by doing this integral, what you get is the density function, the distribution function. Now, the density function if you want to get, then you will have to differentiate it, right. So, rather than that, here is a general way of getting the density function, right. So, what does it say? This is again principle wise it is not complicated. So, what is the density function? That is f let us say previously we had taken z and w here, and actually I have, this is a human error because I have taken this part from a different book. I mean, without recognizing I have gone to a different notation. So here we are talking about f of vw is equal to the probability that, actually we should say dv dw, is it not? That is, what is the probability that capital V is between V plus dV and V, and capital W is between W plus dW and W. What is that probability? That probability is nothing but this joint density into dV dW. dV dW is the area. Density into area will give you mass, area or volume, right. So basically what you have to characterize is this probability, that is what you have to characterize, and you have to get it in terms of x and y. That's the thing, right. So now what do we do? Now you see that if we now have two spaces, okay. For example, you have a space called VW and you have a corresponding space of xy. This is y, this is x, this is v, this is w, or maybe this is v, this is w. So what are you considering? You are considering an elementary volume which is dV dw, and this is v and this is w. So you are considering the probability, you are basically integrating the function over this. Now if you have to find out the, now this corresponding to this, that where from this has come from x and y. So you have to identify that which is this region in x and y which has given rise to this region in v, is it not? You have to find out the corresponding region in the xy plane. So and you have to integrate the fxy function over that region, agreed? So in general what will happen? Now that you can do, for example this square, that is where v is less than or equal to this and w is less than or equal to this square, in general maps into what? In general maps into a parallelogram. Actually I have drawn it, I shouldn't draw it like this, I should draw it in a general case it will be arbitrary. It will be an arbitrary parallelogram. Huh?
It might be a curved area also, like.
It may be actually we are considering it as a parallelogram because we are considering differentials, because they are so small that curvature, that amount of difference is actually a higher order differential, so we can ignore it, okay. So now what are the coordinates of this, that you have to find out. So the coordinates of this are, obviously one of them is going to be xy. Basically what we are doing is this function, if this function is one to one and differentiable, when can functions be inverted? That is, if you have y is equal to gx, when can you write x equal to hy? That is the same relationship when they are one to one. Otherwise you cannot. If it is many to one, then you cannot invert it, right? So if it is one to one and differentiable, assuming we are taking a case, then you can define the same function maps you can invert, and you can write x equal to phi vw and y is equal to psi vw. That is, I am doing different. Previously I was saying v is equal to gxy and w equal to hxy. So I can invert them, right? So now it is now simple, because once why I came, because I am going from dv dw to the corresponding increments in the xy plane. I want to identify them. So now once you have defined these maps, this parallelogram coordinates are going to be, one will be x and y, that is given v and w, one coordinate is going to be x and y, that is phi VW and psi VW. The other coordinates are going to be this, it will be x plus del phi del V dV and del psi del V dV. Basically what are these coordinates? This coordinate is V, this is V plus dV. So what is the coordinate? So this coordinate is VW, this coordinate is V plus dVW. So corresponding to this V plus dV, both x and y will change. So by how much will x change because of this dV? X will change by del phi del V into dV, because x is phi VW, right? By how much will y change because of this dV? That will be del psi del V into dV, because y is defined by the psi function. Similarly, if you take this coordinate, that is V W plus dW. So now W is changing. So now if W changes, then by how much again x and y changes? Now it is del phi del W into W and del psi del W into dW. So these are the corresponding coordinates we are getting, and finally here you get both V plus dV and W plus dW. So both are changing, so you have to add their corresponding things. So now you got the 4 coordinates points on the xy plane. Now you have to find its area. So what is the area of this? The area of a parallelogram is, suppose this is A, B, C and D. So and suppose this is say phi and this is say theta, then what is the area of this parallelogram? It is AB, it is AB, I hope you can see it. It is AB into this one. So this angle is theta minus phi, this is AC. So it is AB into AC into sine of theta minus phi, that is the area of the parallelogram. Agreed? So now sine theta minus phi is what? So it is AB into AC into sine theta cos phi minus cos theta sin phi. So now you can say that it is AB sin theta into AC cos phi minus AB cos theta into AC sin phi. Like this you can. Now if you find out these, now what is rather one second, rather we will say we will combine them differently. No, but we can do that same thing. Now you see what is AB sin theta? AB sin theta is this one. AB sin theta is now let's yeah, we should do it the other way. We should combine AB with cos phi and AC with sin theta. Then AB cos phi is what? AB cos phi is basically the x coordinate change between this point and this point. So what is the x coordinate change between this point and this point? That we know. Suppose this is P1, this is P2, then the x coordinate change is between these 2 points is del phi by del V into dV. See, I am trying to find out a general thing. Why and of course it is not fully general in the sense that it is not in n dimensions, but in 2 dimensions I am doing a general thing. So if you now simply calculate these terms, what you will get eventually is this. What you will get is the, where is that? Okay. What you will get is the area is, let us see. So now what you should do is, just a moment, let me see, otherwise I might miss something. I should have it somewhere here. Yeah. So, now, so what we have is that finally the probabilities must be the same whether you are computing it in the VW space or whether you are computing them in the XY space, probability should not differ. So, therefore, FWV into this small area dVdW, which I am given the name area in the VW plane, must be the same as Fxy into xy into Axy, the corresponding area in the xy plane. So now we can compute this one in terms of this one and this area ratio. Now you can just work out using the principles that we have said just now, and you will get that Axy by AVW is this quantity, which turns out to be nothing but the determinant of this matrix. Del psi by del v. If you take this matrix and if you take its determinant, then you will get this into this, this into this minus this into this, that is this one, right. So, this formulation actually gives us, actually from this you can really generalize it in the sense that if you go to n dimensions, it turns out that you will get an nth order determinant. Simply this matrix will become nth order. That can be proved. Of course, the proof is much more complex, but the idea of putting it in this form was to extend it for n dimensions, so that you can even compute the interrelations between n random variables. So this is how you can directly calculate, that is, given the phi's and the psi's and given the density function. See here we are not going through the distribution function, directly from the density function and the phi's and the psi's we can calculate the density function of the derived variables. So, and then conditional distribution is the same thing. For example, what is the probability that of y given that x is less than or equal to x, such things. Obviously, it is this is base formula. So, this y is less than or equal to y and x is less than or equal to s divided by x is less than or equal to x. So, this is this. So, we have here is a small example which is one of the very main cases that one should see. For example, I mean z is equal to x plus y, because this is one of the most common way of combining two random variables that people would like to do. Simply add them. You can extend this result easily to adding with weights and adding n numbers and things like that. That is very simple. So here what they are doing is, again, so what if z is defined in this way, so what is going to be the distribution function? It will be the integral over a region. Over which region? What is now my dz? I was saying that you have to integrate over a certain region dz. So what is the dz now? Now the dz is those set of points x and y such that x plus y is less than or equal to z. So basically it is, if you have the xy plane, so this is your 1 and suppose this is your 1, suppose you are having z is equal to 1, then this is your x plus y is equal to 1 line. So you should integrate over this region. For all points on this, x plus y is going to be less than or equal to 1. So like this, for different values of z, you are going to take different set of straight lines and then integrate over the corresponding region. Correct? So now what is going to be this? Obviously, if x plus y is z, then what is x? X varies between minus infinity and z minus y. I am actually eliminating one of the variables. 3 variables are not needed because they are actually related by one equation. So you can use one equation to eliminate one variable. So I am now eliminating it. So the limit of x becomes z minus y. So what is going to be this? This is going to be, if you take the indefinite integral of fxy, if you denote by this gxy, then it becomes z minus y y and minus gxy minus infinity y. Simply put in place of x these two limits. If this g function is the indefinite integral corresponding to this, then how do you get a definite integral? Just by putting the limits. So you have this is this. Now gxy of minus infinity y must be 0, because no number can be less than minus infinity. So this term is gone. So you have only this term. Now if you want to, if you are interested in the density function, then you have to differentiate this. So you put it in, and finally obviously because this is supposed to be the indefinite integral of this. So what is going to happen? D dz of gxy is equal to d dx of gxy into dx dz. Now d dx of gxy is what? Nothing but fxy, because fxy is the indefinite integral of, I mean gxy is the indefinite integral of fxy with respect to x. So if you differentiate this with respect to x, you will get back this. So this part becomes this, and what is x? X is z minus y. So d of z minus y dz is 1. So you get 1. So you get only this term if you get the density function. Now here what we did is we first integrated x, then we integrated y. Nobody tells you to do that. You can also do it in the reverse order. It's all the same. So then if you do it in the reverse order, you will get nothing but fxy x and z minus x. Here you had eliminated the variable x by integrating first. You can also integrate you can also eliminate the variable y. There is no, you can always do that. So then it will be this, and if these variables are independent, that is x and y, if they are independent variables, then their joint distribution will be replaced by this part. It will simply be the product of the individual distribution, individual densities, and this is what is known as a convolution integral sometimes. So this is a special case, just to demonstrate that how you can get a special case when this function is z is equal to x plus y, which is a common function. So as I was telling, we'll stop here today. As I was telling that next week we'll have tutorials, and though I am teaching all kinds of theories, and which may seem a bit abstract, but what I expect is that you will apply the theories. I am not expecting that you are going to memorize these theories. It's not at all needed, though the theories I am teaching. So what I expect from you is that you will read the theory and you will be able to apply it in a situation. In other words, it means that you will solve problems. So the set of problems is very simple. I have got 2 books here. They have got nice exercises, large number of solved examples and exercises. So I expect that you will solve them, and in the next class, next Tuesday, we are going to have tutorials, 2 hours, where I will try to solve only those problems that in general you could not solve. So the ball will be in your court. You will have to point out to me saying that, sir, I could not solve this problem. It's not that I will come and solve another set of, because this already contains a number of solved examples. So I am not going to redo another set of solved examples. Okay. So if you don't point out problems, I will assume that you could solve everything, and then we'll have a nice off on that day. All right.